Welcome back, everyone, to the afternoon session. And we are happy to have Ioana Coman, which is going to talk about VOA from 3D and for non-abelian quiver cage.
Yeah, thank you very much. So, okay, I guess I should say, first of all, a little bit of the wider background for this story. Essentially, with my collaborators, so Myung-Bo Shim, Masaki Yamasaki, and Yahao Zhao in IPMU, we were working on concretely constructing vertex operator algebras from 3D SQFTs. And vertex operator algebras, VOAs, they represent an algebraic structure that has become quite ubiquitous in SQFTs in higher dimensions, so 3-4 dimensions higher. And how VOAs appear concretely, this depends greatly from context to context because they can appear either on an associated auxiliary two-dimensional surface, or they can be embedded into the physical space of the SQFT that one is studying. So here, this is the second such context. So here, concretely, the 3D theories that we have in mind are 3D n equal to 4 theories T of Q that are associated to a quiver and which are on a background that's essentially can be seen as a line times a holomorphic curve. And it can be thought of as this three-dimensional space where in the bulk there's the theory T of Q, and then on the boundary, on C, lives the VOA V of Q. And now this theory, I said, they are three-dimensional n equal to 4 non-abelian quiver gauge theories, and they have a topological H-twist, which makes the twisted theory topological in the bulk and holomorphic on the boundary. So now the point to construct these VOAs is to start with the quiver data. So quiver, I've drawn a local portion of the quiver. So we'll have two components, the nodes and the arrows. The quiver will also have an associated Cartan matrix, Cij, which is 2 times delta ij minus the number of arrows between the nodes I and j. And I'll have two-dimension vectors, gauge 1, which will be composed of non-negative integers and a framing dimension vector, which can be 0 or greater than 0. And these numbers, they will satisfy one condition. So combining them into a vector, the condition is that the framing vector minus the Cartan matrix acting on the gauge vector, these need to be in Z greater than or equal to 0. And so in terms of this data, what we associate to the quiver, well, there's a physics side. What it translates to. I'll come back to that. For now, we can just take it as an input. If on the right-hand side it's 0, this is what gives balanced quivers. If it's not 0, what it translates to physically, because here we have the theory, it has a boundary. One more thing I should specify, also deformed n equal to 0,4 Neumann boundary conditions. This theory can have boundary gauge anomalies. If this is equal to 0, then the non-abelian boundary gauge anomalies vanish. If it's not equal to 0, they need to vanish by adding additional matter fields on the boundary, additional Fermi multiplets. But so now, coming to the data that we use, so data.
Is this a conformal condition that some data function?
It's an anomaly cancellation condition.
More like anomaly. In 2 dimensions,
It's
because usually this is in 4D it is related to conformal.
I know, but this is 3D.
More like 5D, yeah, where it's also some kind of anomaly condition.
It has different interpretations depending on the dimension where you work, and also this comes in how I say H twist, topological twist, how exactly you construct the supercharge with respect to which you take the twist. That also changes with dimension. So this is part of the physics that I will not discuss. I will just say that from this setup, the data that one has is G, which is a reductive Lie group, complex value, so GL VI I in Q0 on G. So this is a complexification of the corresponding gauge group. There will be M, a symplectic representation of G with mu moment map. And potentially, possibly, some representation R, fundamental or anti-fundamental, of this group. So physically, the data that is associated to the quiver, there will be n equal to 4 vector multiplets associated to the nodes, and there will be hypermultiplets associated to the arrows, plus whatever additional boundary fields need to be added to cancel any gauge anomalies. So now in terms of this data, the aim is to construct a VOA V of Q by the BRST reduction of some VOA defined by the boundary fields, so in terms of G and M, BRST reduction with respect to the action of the group G, where this V hash is defined by the boundary degrees of freedom. Now this is for now still very vague, and people have attempted this. There are multiple works in literature where people have focused on abelian gauge theories and constructing this explicitly. Now what we did with my collaborators is specifically look at non-abelian gauge theories, and the idea was not to just study this boundary VOA V of Q physically just by constructing currents. So this is maybe I can say the first highlight of what we did was to construct the VOA explicitly from BRST closed operators. And what this gave are explicit homomorphisms from affine W algebras into the boundary VOAs. And I will say more about what these are depending on the exact quiver data and examples. But 2 was the mathematical construction of the boundary VOA from chiralization, starting with an associated classical geometry. So here M of Q is the quiver variety or the Higgs branch of the theory that we start with. And on the other side, there's the VOA. In one direction, the relation follows from chiralization. On the other direction, one takes the associated variety. And then from this procedure of chiralization, working locally, so localization, this allows to find the free field realizations. Of this V of Q. I will explain when I get there. So this is a preview. These are the two things that will come out. Chiralization is literally taking the functions that classically parameterize a ring of functions on the associated variety and turning them into BRST closed operators, so chiral fields that generate the VOA. So now, with these two as the 2 points that I want to highlight, I can start first with just telling you about the classical part of the story. So just for the quiver variety, which is a Nakajima quiver variety. So starting with the quiver, there is the representation space, which consists of maps between the vector spaces associated to the different nodes. So WI means that the associated vector space WI can be considered as C WI, and similarly here for the gauge counterpart. And here the arrows, let's see if I get them correct. There will be alpha I, so there will be 4 maps, beta, x, y, I. And on the map, this will be alpha I. This will be x, A, from I plus 1 to I. And similarly for this arrow. And then the beta and y will be the arrows going in the opposite direction. Now on the space, the group G has a Hamiltonian action. And there is a moment map that I will write with a twiddle because it's an extended moment map. It's from T star rep Q, but times a vector of complex numbers, one complex number associated to each of the nodes, into GLV. So here, what are mapped are quadruplets of these alpha, beta, x, y, and the vector z. And these are taken to sum over arrows in Q1, the commutator of xa with y, minus sum over the nodes, alpha I, beta I, minus z. So the way to interpret this, there is a moment map, an extended moment map associated to each node. And the way these, on the right-hand side, the arrows are all arrows that start from one node and end at the same node. So for node I, beta, alpha, you can see goes down and up. And then the corresponding x arrows are also arrows going to the left and returning, or to the right and then returning, hence the sign. And there will be an additional complex parameter which plays the role of a Fayette-Iliopoulos term. This is convention. You can swap the order in which minuses appear. You'll just lead to a symplectomorphism. So one just needs to be consistent with assigning the relative signs consistently to each of the nodes.
Are you taking the advice to be generic?
Here the Zs I'm considering to be generic. When we go to the chiaralization stories, these will correspond to additional Heisenberg fields, exactly, and they will correspond to the inner products of Heisenberg's in the OP.
You want to resolve the varieties.
Of course, I will. That's why I'm putting twiddles everywhere. That's exactly the point of this. So, thank you very much. From this, we get the affine extended quiver variety, which I'll denote with the 0, and which is of Q, whoop, and which is the symplectic reduction of the preimage of 0 with respect to G, and then there will be the Nakajima quiver variety, where on the right hand side I'm restricting to a stable locus. Now the notion of stability simply refers to restricting to maps from the framing nodes to the gauge nodes, which when composed with all the other maps span the entire space. So there is no subspace that is strictly smaller that appears in the Nakajima quiver variety. And now, to give a concrete example of the type of theories that we look at, these are the T sigma rho SUN theories. They have a realization in terms of intersecting systems of diagrams, but concretely the data that defines them, rho and sigma, are partitions of N. For simplicity, and for the relation to affine W algebras, I will take N to be the simple 1 to the N, and then sigma to be, let's see, K minus 1 to the W, K minus 1, I to the WI, 1 to W1. So this is no accident. The W's match exactly the framing dimension integers. And then from rho, V K minus 1 is equal to 1. And then the remaining are V's are exactly defined by CV minus W is equal to 0. So this is the corresponding quivers for these theories, T of rho sigma, are balanced quivers where there's no non-abelian gauge anomaly on the boundary. So for example, taking 2, 1, and 1, 4, SU4, the corresponding quiver that one finds has 3 gauge nodes and 2 framing nodes. 1, 2, 2. This is I equal to 3, 2, 1, 1, and 2. And for these partitions, the Nakajima quiver variety, non-extended, is just the Slotowee slice associated to sigma. So for sigma, there will be a corresponding nilpotent element F in the Lie algebra, whose Jordan block is specified by this partition. And the corresponding Slotowee slice is the intersection of the nilpotent cone with the nilpotent element specified by sigma and the centralizer of the partner in an SL2. Now, this I'm saying in words and not writing it because it's not particularly important. What is important here is that the classical geometry, this is, do we have any other colors? No, okay. This is parametrized, so the ring of functions on M of Q is parametrized by functions associated to paths which go from which go between framing nodes. So these are gauge invariant. So concretely, there will be one path from the first framing node to itself and two paths that go between neighboring ones. And these are the only three paths that need to be considered modulo moment map relations. So now, from the data that we have and having the parametrization of this classical geometry for the ring of functions on this classical geometry, the next part is precisely the chiaralization, actually constructing the VOA globally. So chiaralization promotes the maps to fields of the VOA before performing the BRST reduction. So if I locally have the node I, again, this will be in general. So assuming that the quiver is not balanced, there will be nodes, there will be fields I, J. Let's see. So the V hash VOA will be formed by a beta gamma system. So these will be I, J for all the nodes, and XY for all the arrows. And these are matrix valued, so the OPE will be, for example, for, let's say, XA, we will have two matrix indices alpha, so this will be in the target group, and this will be in the origin with respect to the arrows. And the OPE will take account of this. And the part that has poles will have the corresponding delta functions. This will be at Z, W, Z minus W. Similarly, now there will be a fermionic system from the BC ghosts. For each node of the graph with a corresponding OPE. If the quiver is not balanced, each framing vector space will be promoted to have a fermionic counterpart with arrows. Let's see, phi, psi. So there will be a free fermion VOA. And then these integers f are defined precisely by what was left free on the first blackboard. So the difference between the framing dimension vector and the Cartan acting on the gauge counterpart. And there will be H Heisenberg VOAs associated to each of the nodes. So here, what I was calling V hash will be exactly the tensor product of this beta gamma system, the free fermions, and the Heisenbergs. And now I'll erase the example and keep the classical part on the right-hand side with the representation space and the moment map. And right here, the chiral analog for the moment map. Alpha, beta. Now this will be a G current for the ith node, and explicitly it will be given by the chiral counterpart of this equation. So here we take a sum over arrows whose head is J, so X, Y, alpha, beta, plus sum over arrows whose head is equal to J, and then opposite order. There will be the beta gamma system associated to arrows going from the framing node to the gauge node and back. Potentially the free fermions if they exist. And the Heisenberg fields. Times the identity. And here, writing this out, what it gives an SU VI current, removing the trace component, and then the trace part is an anomaly-free U1 current. So this is, it defines J U1. And this current has level -2 times VI. And this is only true because of the anomaly cancellation condition that I had before. Now, why this matters? Because this defines the BRST nilpotent element. So at each node, this is a contour integral between the chiral moment map. Let me write it like this. So the BRST current, where the BRST current is contains one of the ghost fields, it has the chiral moment map. And then there's another contribution from just the ghost fields. And this current has exactly the level 2 times Vj and cancels the non-abelian gauge anomaly coming from this current, which means that di squared is nilpotent. So this is the counterpart for the chiral for the chiralization of this story, so for the VOA. Now, the VOA then is defined the quiver VOA is defined as the zeroth relative cohomology of the boundary VOA that I had there, tensored with the VOA coming from the BC ghosts with respect to D, where D is equal to sum over I in Q0 of all of the DIs. And the relative part comes from looking at the subcomplex, which is annihilated by V0. So by the zeroth mode of the B ghost, and J0 alpha, which imposes gauge invariance. And now in the chiralization process, generators of the ring of functions on the quiver variety are mapped to generators of this VOA, which are BRST closed. And concretely, going back to the example that I had, 1, 2, 2, for the T-row sigma theory, I said there that there were 3 maps necessary to consider going from framing nodes to themselves. And these, we have 1, 2, 3. Let me call this one G12 and this one G21. So G12 is exactly the counterpart of the classical variance, so J1 x I2. Yep. Mm.
Do you define the VOA to be the 0 degree, or you have some vanishing?
No. You have to prove that the higher degree cohomologies vanish.
Yeah. So, and you can prove that.
Yes. Yeah. That part is not complicated. Yeah.
So what happened with the structure of this permanent drop? And there's some of them beta, right?
Sorry?
And there is the formula for the moment map, and there is a permanent drop on the web bar.
Here.
What's the index structure of this drop? Like, where is alpha and beta?
Oh, it's the same as where did I write? I still have. I mean, this is still matrix valued. So in terms of OPEs, it's exactly the same as for the XYIJ. It's still associated to arrows between vector spaces of dimensions VI and FI. So the point I wanted to make is going between different framing nodes, the chiral fields that correspond to those are exactly the analogs of from the classical story. So this will be J2, Y, I1. However, between starting and ending at the same gauge node, this is not BRST closed, and it gets a Heisenberg contribution. H, well, IJ. And now with the additional correction, so here, Heisenberg field, this will be BRST closed. And what we have found with Myungbo, Masahito, and Yahao is explicitly a homomorphism from these generators and also some U1 counterparts that I'm not writing into an affine W algebra. And this will be in general, minus n plus 1 GLN F determined by sigma into V of Q of T sigma 1 to the n SUN. So the corresponding quiver for this theory, where F of sigma is precisely the nilpotent element defined by the partition sigma. Now this, for the example that I've just presented, the strong generators of the affine W algebra can be found explicitly in literature. They have been studied together with the OPs that they have. Now the index structure of these guys makes it easy to deduce what their formulae are in terms of these currents. For some of them, not all of them, but the remaining ones can be bootstrapped. So, okay, perfect. In this way, we have this explicit homomorphism. Now, this is still, at this level, one could complain that it's not very systematic. So why follow this route? And this is why in the second part of the story, the mathematical side, we look at localizing these vertex operator algebras and try and find a way to analyze the boundary VOAs systematically. Any questions while I'm erasing? So now for part 3, systematic analysis. There are two parts to this. One is localization. And the second part is the quiver reduction. Now, localization, a recent paper that looks at this is by Tomoyuki Arakawa, Kuwabara, and Muller. So this is 23. But then the tools used there go further back to a paper by Kuwabara, and then even further back to Arakawa, Kuwabara, and Maliko. And they give a counterpart to what I've presented so far. So on one level, what I've shown for defining the boundary VOA, this already appeared in earlier work by Costello and Gaiotto from 2018, with some earlier work of Gaiotto. And then subsequently, There are many people that worked on this in various combinations, Thomas Kreutzig, Tudor Di Motte. I mean, we have other colleagues in the audience, Andrea, who have also worked on this for the so-called rank zero theories, for example. Now, what this mathematical counterpart does, localization, here looks not at VOAs, but H-bar-adic VOAs. The H-bar-adic being introduced as a means to enlarge the vertex operator algebra that one looks at by including an inverse of a function, which then poses the risk of having unbounded poles in OPEs, and that's where the H-bar parameter comes in. And localization then allows to restrict to open patches in the quiver variety and give rise to the localization. So let me just say part A, what this does, localization. The punchline is that it defines a vertex algebra on the quiver variety from the global sections of a sheaf of H-bar-adic VOAs. Themselves constructed from BRST cohomologies. So, as a formula, let me write this and then I will explain. So instead of working over the entire affine variety, this will be an open patch in the Nakashima quiver variety. R will be exactly the representation space that I had earlier times C to 0. And then U will be a certain open patch in there with some compatibility conditions between U and U tilde. And then the ordinary vertex algebra will be defined from the global sections. The finite part with respect to H bar, and then setting H bar to be equal to 1. And the claim is that there exists a map of supervertex algebras from what I described earlier into this VOA. And this is fairly easy to see the existence of a map when looking before taking the finite part with respect to H bar. Now, I haven't said anything about injectivity or surjectivity yet. That is more subtle, so I will not comment. There are cases where injectivity can be proven. What I will say here, last thing, maybe, just as an example for H-bar-adic beta-gamma systems. So for VOAs, they are defined by a vector space, distinguished vectors in there, the 0 and the conformal vector, and two maps. for H-bariatic VOAs, the vector space themselves, the underlying vector spaces, are not C modules, but CH bar. And the OPEs here, let's see, beta Z gamma W, instead of having just one, they will have an H bar over Z minus W. And as vector spaces here, the C, T star C, H bar is a vector space. This is isomorphic to CH bar. And then what appears also classically, the modes of the beta gamma system acting on the vacuum. Now the reason that I'm mentioning all of this now, this is where this perspective becomes powerful, is because it leads to a quiver reduction algorithm. So locally, I can think of the quiver just as being a gauge node with certain lines connecting it to the rest of the graph, and then a corresponding framing node with arrows. I'll call these specifically, forgetting about indices, beta and alpha. And here I have for simplicity the same integer in the corresponding entry of the dimension vectors. Now we can define an open patch here in the extended quiver variety, where the alpha homomorphism is an isomorphism, which means that here one can use the corresponding moment map in terms of alpha, beta, and then the collection of x and y maps to solve for beta in terms of alpha. So locally, one has then, by removing beta, that this open patch is isomorphic to the quiver variety associated to a reduced quiver times the corresponding vector space associated to the free parameter. So this is Q, and then Q prime just has now one fewer gauge nodes associated to it. Now the chiaralization of this the counterpart is that the corresponding sheaf of H-paradic vertex operator algebras on this open patch is isomorphic, can be mapped to that for the reduced quiver semi-direct product with the corresponding Heisenberg VOA. Now semi-direct product because here there may be other nodes, neighboring gauge nodes, and there is a non-trivial OP between the Heisenberg VOAs associated to neighboring nodes. So now in terms of this, what? Yep.
Should have asked about it. What is H-addict?
The OPs have an H bar dependence. So once
activity is only proportional to H bar.
Exactly, once you take OPs and you include, what does it mean to solve in terms of alpha, which is an isomorphism? There's an alpha inverse. For the VOAs, you have an additional corresponding field that you take the inverse of. Once you take OPEs with the inverse, you can have unbounded poles appearing, but they will all have powers of H bar associated to them. And then at the level of the underlying vector space, it's exactly that. If I didn't have the H-bar dependence, then the vector space will be just given by modes of the beta gamma fields acting on the vacuum. But because there is also an H-bar dependence, this is a module over CH-bar. So the H-bar-adic part only comes into play as a tool for us to be able to restrict to open patches. Because what we do essentially, instead of working with the affine, with the Nakashima quiver variety, we restrict to smaller and smaller open sets that can be just T star C. So it essentially decomposes the VOA under this quiver reduction, which essentially translates to a localization procedure. It turns takes the VOA to a product of beta gamma systems and Heisenberg algebras. Yeah. Okay, so the last few minutes, I just want to show you what the building block is for the a simple building block for this reduction procedure. So here, what I will take, and for simplicity, I will restrict to not have other connections, or maybe we can say that there may be other connections, but we ignore them. So N, I, J, Y, X. We will have OPs between Heisenberg generator associated to the node of our interest and whatever other Heisenberg generator outside of the building block. Now, for I invertible, our block will map to M, N, other things, and then gamma, beta, what I was saying earlier, it reduces to a beta gamma system with another field, alpha. So, adding the determinant of this field, well, the inverse, and then the -1 mode to the VOA, we have an embedding of the chiral vertex operator algebra into an extended one. And with the mapping that defines beta to be I inverse X, gamma, Y, I, and then alpha to be the Heisenberg plus 2 trace I inverse partial I. The corresponding extended algebra decomposes into, let's see how to write this schematically. It decomposes into a part that's associated to the reduced quiver. And the chiralization of T star GLN. So these two components will have non-singular OPs with each other. And this component, R prime, will be the beta gamma system. So it will be generated by B minus N gamma minus N modes, alpha minus N, acting on the vacuum. So now, the last part, in terms of this map, how do BRST, what is the map on BRST closed fields? So I will have here n, n, and n. And to such a map, this is yi. It's simple. This one will be jx. Then there will be this ji, following the same arrows, minus trace ji to make this gauge invariant and identity. And then the last one, yx minus trace yx times the identity. And now map new will send yi to gamma. Jx will be minus beta gamma minus alpha times the identity. Yi, just give me a second here. So we rewrite the BRST closed fields in terms of the new fields, beta, gamma, and alpha. And what this gives, when we specialize then to n equal to m equal to 1, it gives a Akimoto realization of the universal affine algebra for this system. So m equal to n equal to 1, we get a map from v minus 1 of SL2 into mu of q, and under this map to the free field beta gamma tensor Heisenberg, which maps E to yi and then gamma f h. This is jx. So we find Akimoto realization in the most simple of cases, which has just 1, 1, 1. And we can compose maps into the VOA that we have defined, and then the free field realization. And from the fundamental building block that I've shown here, one can go more general to have different dimension vectors, look globally for more complicated quiver varieties, and systematically apply this reduction procedure. That's it.
Any questions or comments for Ioana?
Yeah.
Basic one.
Mm.
But this process of chimerization can be thought like a sort of physical, meaning in the sense that it's so pretty theory at the boundary of the.
Yeah, exactly.
So it's a theory of maps from the boundary to the Nakajiman variety. But I mean,
Yep.
is it supersymmetric?
No, I very much doubt it. I mean, it depends what you mean by supersymmetry. The boundary conditions are 0,4. and they're deformed, so they're really 0,2. Now, what we looked at specifically is the bosonic part. I said in general there will be fermions. There will be some fermionic extension of what we see, and there is one very simple abelian example where the author took the types of fields that I was writing, composing maps, and replacing one of these by so non-balanced case, replacing that map by a fermionic counterpart. And then trial and error showed that once you take enough generators of that kind, the OPs close, they don't generate anything new. But that part of the story is much less explored in general.
No systematic way from physics to construct this theorization. We do really
Well, you can go ahead.
Oh, yeah, I think the idea is you can see that the boundary VOA is defined as a VRST reduction from the fields which are chiral counterparts of the symplectic reduction that defines the X branch. But then you have to ask yourself the question whether VRST reduction commutes with chiralization commutes with VRST reduction.
That part is extremely non-trivial, and that's what I said in the middle, that there exists a map from V of Q to the chiral, where exactly V of Q was constructed globally, the chiral was constructed locally.
Okay.
So it's like you have the which is the LST reduction, and you can interpret this as a chiral analog of some symplectic reduction. If then this commutes, then you know that you get a chiralization of the other functions on the X branch. But from a physical viewpoint, I don't think there are better ways than this to say.
So there is no way to compute, say, some conformal blocks or anything, holomorphic blocks?
Oh, that's the next level. Like at this point, we are still trying to understand exactly what the VOA is. As Andrea said, just to say what it is, that you have some fields on the boundary, by definition, they will define a VOA, and you do BRC reduction, fine. And then what?
You can expect the conformal blocks to be related to the space of states. So
yes.
SQFT on Riemann surfaces.
Yeah, it's related.
But even to prove that in rational cases that this is true took 30 years of technology.
Yes, and these are not rational. What I'm discussing here already are beyond that.
These are all logarithmic.
Which makes them nice. Which provides a connection at the next level. So what we have now is explicitly we see the affine W algebras. An extension of these are the log vertex operator algebras that are extremely interesting from number theory, representation theory, like many points of view, which is why this is an entry point to a much bigger and more exciting story. So I don't know, we probably won't hear about it this week, but even here, I specifically said at the beginning, H twist, not C twist, or A versus B. So one can ask questions about mirror symmetry, how this arises here for theories that are self-dual under mirror symmetry. So just the TSUN, how that arises at the level of the VOA. And it's a very non-trivial story.
How it's formulated in terms of VOA. What means that if you feel there is self-dual.
So you expect it on physical grounds, but then the VOAs themselves.
Part would you expect that it should be the same?
Well, on the other side, it'll have a very non-trivial realization because you'll have monopole operators that need to be included, for example.
But depending on the boundary conditions, you expect them to be more equivalent. You expect them to have the same category of modules.
Exactly.
But depending on the boundary conditions and which boundary degrees of freedom you're adding to cancel anomalies, you might get different VOA.
Exactly.
But
you get very non-trivial, interesting dualities arising. Okay.
Like, I mean, I worked on a similar story in the Abelian case with Crispin early, before the Kuwabara paper.
Yeah.
Really using things, but
no, but you also had a localization story.
Yeah, indeed. And the question is, like, one of the things that got me interested into this is that the field realization
okay, this matters, I think. So far, I said we had Heisenberg VOAs associated to each of the nodes. Concretely, if you want to discuss those, you need to actually realize them in terms of beta gamma, in terms of fermions. And those, there is no unique way to cancel the U1 gauge anomalies.
Yeah, because finally the most remarkable equilibrizations we were getting in the Dylan case were the ones where we were not resolving the associated variety at all.
So you still had singularities?
Yes. But
doesn't that, okay, maybe we can, yeah.
Any more questions or comments? If not, let's thank Ioana again.
Thank you very much.